Okay, let's get started. It occurs to me that I sort of assume most of you know graphically what integration and differentiation are. I think that's probably true, but it's probably better to confirm since it may have been a while. There's possibly been a lot of beer between when you took it in high school and today. So let's figure this out. Okay, if I give you a curve that looks like this, and actually let's take a curve that looks like this, okay? And I will say I start at this point, and this point is minus infinity, and this point where it actually reaches 0 happens to be plus infinity. And I ask you to find the integral of this function, which I'm going to call I. And I ask you to do it graphically. I don't want to know what the math is. I just ask you to do it graphically. What would you be doing? You'd be taking the area under the curve. Okay, good. Now, let's take another case. Let's take a case where I have defined this function such that this is my 0 point, and I've set it 0 to the left of 0. I'm doing the same thing, right? But I get to now take advantage of a certain fact. I take advantage of the fact that the integral to the left of 0 has an area of 0. So I can write that the integral of I from minus infinity to infinity is equal to the integral from 0 to infinity of I, because I is equal to 0 for all the x less than 0. Oh, thanks. Let's keep it here. Okay, so that's essentially what we did at the end of the last class. All right, we took advantage of that fact to set up this equation, where we essentially said, let me turn off the stage light here. Okay, where we said to calculate the total amount of charge for this equation system that we had set up earlier, we wanted to find the amount of charge as a function of time. Now, what is charge? Charge is the integral of current with respect to time, because time is, current is charge per time. So the integral is therefore necessarily going to be charge. So, at the end of the last class, we said this fact. We said the charge is going to be the integral of the current with respect to time from the start of our measurement, which was minus infinity, to whatever time we care about, which is t. So our first equation was q of t is equal to the integral from minus infinity to t of I. That's what we started with. Then we took advantage of the fact that that integral can be rewritten based on this fact, namely that we know that I is equal to 0 for all x less than 0, or where x here would be t. We can rewrite this integral, instead of going from minus infinity, we can rewrite it from 0 to t. The nice thing about writing it from 0 to t is we don't have to deal with this weird discontinuity that shows up right at 0. Okay? So we just integrate from 0 to t. We plug in the equation form that we had, and that gave us an equation for the charge as a function of time. Okay? So that's the first part of the problem, and that's where we ended the last class. Okay. The second part of the problem is to find a specific change in charge. In other words, I want to know the change in charge, the change in the total amount of charge, not the instantaneous charge, the change in the amount of charge between 2 points, time point 1 and time point 2. Okay. So I want to find delta Q at time point 1 relative to delta q at time point 2. So we will write that as q at t2 minus q at t1. That will just be this integral. The integral from minus infinity to t2 of I minus the integral from minus infinity to t1 of I, which of course we can just rewrite as the integral from t1 to t2 of I. Plug it into the equation where the upper limit of the integral is 2, the lower limit of the integral is 1. Solve it and you find it is 4.45 coulombs. Okay, let me ask you a question. Go back to the curve. Look at this curve right here. The current drops with time. Yet, delta q 1, 2, or delta q 1, 2 was a positive number. Why? Yeah. Yeah, the areas are positive. Even if even if this is dropping down, the incremental area going forward that's subsumed by the curve gets larger. It's as simple as that. There's a handout here if you don't have one. Okay. So we'll get to it later in the course. So if you don't have one at the back, I'll pass them back again later. So that's a simple answer. That's right. Now, there's not a lot of math in this class. Okay, there's some. But one of the things I'm going to kind of assume that you know, well, I'm going to assume you know how to add, okay? I will assume you know how to subtract. Multiplication and division are a positive thing to know, okay? You're going to need them in the very next section. You're not going to need integration or differentiation again till we get to the section involving capacitors, etc. But you will, in this course, you will have to know how to solve differential equations. Very simple ones, but you will have to know how to solve them. And I am not going to teach you how to solve differential equations. Okay, so I'm going to assume you know how to do that. Nothing really complicated, relatively straightforward differential equations of this type. Okay, so that's the end of a first example. Before I forget, now that everybody should be here, there's 2 announcements I want to make. First, for those of you who are in the Monday lab, don't worry. I know it is a holiday on Monday. I do not expect you to show up for lab. Okay? Essentially, the week is going to shift. What's going to happen is your Monday lab from this week will happen the following week, which means the lab week shifts from Tuesday to the following Monday. And then later in the semester, it turns out we have a Thanksgiving holiday on Thursday and Friday, so it's going to kind of shift back a little. So it'll just work itself out. We have enough slop in the schedule that'll work itself out. We will not force you to attend makeup labs. You do not have to worry about it. Okay? It'll work out. First announcement. Yes, question. Okay, so discussion will just be canceled just for Monday. Okay? Is there a discussion on Monday? I don't remember. Yes, okay. So the Monday discussion is canceled. You are welcome to attend another discussion. We do not take attendance in discussion. Okay? Which means I encourage you to go to discussion. The TAs will actually work through some problems in discussion, which may help you on homeworks and in tests. Okay? You're welcome to go to another discussion. Or if you find you have questions that you're not able to address in discussion, shoot me an email. And you can either come and see me during office hours or schedule one-on-one time with me. That's fine. Okay? So the format of the discussions is basically going to be the TAs taking problems of the type that I'm just briefly mentioning in class and kind of working through them. They're going to go through the exam. Each chapter in the text has several problems at the back of it. Okay? The TAs will take a few of those problems and we'll work through them as examples for you. Okay, that's the idea. So you'll get an idea of how to deal with problem solving. That's what the format of the discussions is for, mainly because given the amount of content we have in this course, we're not going to work through that many problems in class. And it is good for you to see how problems actually work through before you get it on a homework or a test. So that's why we'll do it that way. Okay? But the Monday discussion will be canceled. The rest of the discussions will continue. The first week of class, we never have discussions. Okay? So you're not missing anything from this week. It's just Monday's discussion. You're welcome to attend another discussion. Yes?
Sorry, just the mic is off or something.
It's off?
Just put out.
It did? Yeah. Okay. Gone? Gone. No charge. That appears to be entirely and completely dead. Wait! Bad switch. That's my theory for now. No, it says that. So yes, it is out. Is there anybody listening out there who's doing webcasting? Is anybody inside the box? So. Alright, listen. I'm just going to shout. I'm going to shout. We will manage. If someone, I don't know how they actually do this webcasting, okay? But it is showing up on the web. Someone is clearly on top of this. So we're just going to manage. Okay, if we're lucky, someone out there hears this and comes and gets us a new battery for the mic. Can you all hear me at the back? Okay. Most people don't complain that I'm not loud enough. So I don't expect, well, except for my wife who complains that I'm always too loud. So this is going to be fun. All right. So getting back to the point, discussion will be of that format. For the lab, don't worry about it. It'll get made up. And then there was no homework given this week. That was intentional. I haven't really taught that much yet. Okay? There will be a homework next week. It'll go out on Wednesday. And it will be due the following Wednesday. Okay? You'll get a week for it. And I have decided when the first test will be, and I will tell you that now. The first test will be on the 28th. Yeah. The first homework is sort of a mix. It's going to cover the intro plus a little bit of resistive circuits. Okay? And so the first test will be on the 28th of September, this month. Okay? Okay. So, any other questions, concerns? All right. So we've talked about current. We've talked about charge. Yeah, question.
Tests in class?
Yeah. All tests are in class. Tests are open book, open notes. Okay? This is not a memory exam. I really don't care whether you have the books in front of you or not. Not look at the textbook when I write my questions. Okay? I just sort of look at my notes and what I said in class. And it is, however, going to be, you will not need a calculator. You're welcome to have one, but I guarantee you will need one. Okay? And no cell phones. So if you have a calculator that you want to bring, it cannot be a cell phone calculator. Okay? That's the only rule. Okay. So let's talk about voltage. That's the last thing, the last piece of the puzzle we need to start talking about resistive circuits. So, what is voltage? Well, really, that's a bad question to ask. I should ask, what is voltage difference? Because voltage on its own is a relative term. If I say something is, actually, let's take an example. Let's take a plug point. There's got to be, okay, there's a plug point right here. Okay? What is the voltage of the line that we use here in the US? Yeah. Okay.
The differential potential,
And what is it?
110.
Okay. Okay, let's talk about that. We've got to an interesting point. 110 volts. That's a good answer. Okay. The nominal main supply voltage in the United States is 110 volts or 120, depending on who you talk to. Okay. It's nominally 110. Okay. What does that mean? It's AC. We've already said that. So, what does 110 volts mean with respect to an AC line? Yeah.
Maximum value of the sine wave, like a curve, is 110.
Is it? Is that right? Is that the right answer? He said the maximum value of the sine wave is 110. That's a good guess, but it's not quite right. Yeah.
Isn't it the root mean?
Yes, it's the value of the root mean square is 110. Okay? The peak value actually goes above it. All right, good. Now, what is that measured relative to? 110. So we said voltage is a relative measure. What is 110 measured relative to? It's measured nominally relative to ground, but that's not quite right. What is it actually measured relative to? Yes?
Between the 2 points.
Between the 2 points?
Yeah.
Yeah, what is that other point called?
No.
So one of them is live and the other is? No, it's not ground. The third one is ground. The little thing that's sort of kind of shaped like a U is ground. The 2 flat pins, one is called live and the other is? Neutral. So the measurement of the potential of the voltage is between live and neutral. It is the measure between the 2 points. One is called live and one is called neutral. Neutral should normally be at ground. It's not guaranteed to be at ground, and if it's not at ground, you have a problem in your household grounding. Okay? So, what is the difference between neutral and ground? If you were to, any of you ever ripped up wiring in your home or you've seen it being done, what's the difference between neutral and ground? Why do we have neutral and ground? What's the point of that? If neutral and ground are nominally at the same point, why do we have 2? Yes?
Zero charge and the ground and zero charge. That's right. If the charge is 0.
Well, nominally, maybe, I don't understand what you mean. Try to explain it a little bit more.
If you're trying to say what's the difference between ground and neutral.
Uh-huh.
I mean, I said because they both, when you say they have like pairs, it absorbs the charge. That's
Uh-huh.
why they have a zero charge. That's why it's called a neutral.
Let's assume we don't have anything plugged into them at this point. So we're not talking about current flow. Yeah.
The ground is usually not shielded and the neutral is.
On the inside.
Yeah.
That's absolutely true. Why is that?
There's not a current through the ground.
That's right. That's what he's getting to. Under normal circumstances, we do not want to put current in ground. So, again, you have these landlords you really don't like, go rip up all the wiring before you leave. You can see this, right? So, open up a plug. The neutral wire is shielded, which means the wire that connects to the neutral plug is covered with plastic. The ground connection is a naked copper cable, and it's usually a solid copper cable. Okay? The neutral plug is intended to have current flowing through it. Okay? The ground line, okay? What is the safety reason that the ground line is there for? Yeah. I'm sorry? A little louder? I just didn't hear you. Power surge. Yes, it's a response. It does help in power surges, but not on its own. It's actually related to something we're going to get to. Okay, let's get to this point now. This is something we're going to see when we talk about resistive circuits. Yeah.
Building up our device that goes to the infinite level rather than 2.
Yeah, you're all circling around the right idea. It's how to deal with the case when something that was not supposed to have a voltage on it, for example, the metal box that your device is in, suddenly gets connected to live or to some subset of live and gets a voltage on it. Okay? Now, here's the point. If I take that wire, let's say I have, okay, I'll give you an example. You have a toaster, okay? Well, most toasters, unfortunately, these days have 2-pin plugs, but let's say you have an old toaster and it has a 3-pin plug, okay? One wire of the toaster is the live wire, and that's connected to the elements, okay, that actually heat up your toast, okay? The other wire is the neutral that's connected to the other end of the element. Okay, so one end of the element, the heating element is connected to live, the other end is connected to neutral. The ground is connected to the box. Okay? Here's the point. Let's say something goes wrong and the live wire connects to the box by mistake. And let's pretend we didn't have a ground. Now what happens? What happens when you touch the box? You get a shock, right? That's not so good. Okay. Let's say I want to save myself. I want to make life a little better. So I don't have a ground, but I'm going to be really smart, and I'm going to say, I'm going to connect the neutral to the box. Okay, I'll do that. I will connect the neutral to the box. The neutral was nominally at the same voltage as ground. I connected the neutral to the box. Am I safe? No. Why not? What's that? The entire box could have, well, let's draw that. Let's draw that circuit. We are going to draw our first circuit today. So, our first circuit consists of live, neutral. Coming out here. This is toaster, heater. This is toaster, box. And this is you touching the toaster box. And this comes back there. That's our first circuit. Okay? Live, neutral, toaster. I didn't write that right. Toaster, heater, toaster box, you. Okay? And you are standing on the ground. All right. There's no current flowing through this box nominally. Right? The box is sort of hanging off the neutral line. You're almost right. You're getting there. What are you missing? Anybody tell me why this doesn't keep us safe? Yeah.
When you get to the ground line, like you make another circuit,
Uh-huh.
it can go through your body, so you get.
You're getting there. Remember, this was a wire. And this is a wire that came from a point pretty far away at the generator, wherever the hell that is, right? And you are a low resistance circuit to ground right here. What is a property of a wire that we care about? You've learned this term before. Resistance. Resistance is a parameter that we care about. This wire has some resistance associated with it. When current is flowing through this wire, this point, if there's enough current flow, this point is not actually quite at ground. It can be a little above. And if you are a lower resistance to ground than this is, guess where the current goes? It goes through you. So what is the point of the ground connection to the box? The point of the ground connection to the box is to give a low resistance such that if by mistake the live happens to touch the toaster, it guarantees that it'll have a lower resistance path to ground than you would. That's the idea. So how is the wiring actually done? Does anybody know? In a home, in your apartments. Well, Berkeley apartments are kind of shady. Anybody not living in Berkeley, okay? How are, nominally in your home or in your apartment, how is the wiring done for ground and for neutral such that the safety is assured at the back? Yeah. Go ahead. That's true. One of the things we do is in a home, you are required not through a water pipe, but somewhere in the apartment complex or home, there will be a stud driven deep into earth, a metal stud, which will guarantee a good ground. And when the wire from the utility comes in, the ground point will be tied to that point. Okay? Nominally, neutral and ground are supposed to periodically connect to each other, not within your home, but at certain distribution points to make sure that neutral also stays close to ground. But it's not guaranteed to be low resistance. Whereas the ground point, because there's a nice fat wire that's close to a ground point, close to your home, is guaranteed to be low resistance. That's the idea. Okay? That's how ground works. So, when I ask you what the voltage difference is, it does not mean the voltage difference between the voltage and ground. It really, the voltage on the lines is the voltage between line and neutral, which should ideally be ground. Yes, question?
So where is neutral going?
Where does neutral go? Neutral runs back to the supply line. So it runs back to the generator, ultimately, after going through various distribution points. Okay? It's just not as low resistance, so it may not be quite at ground, especially if there's a lot of current flowing through it. Okay, yeah, question?
I'm just kind of confused because in the alternating current system, like, I thought the electric current, like the voltage goes from like 100 to like 100.
Yeah.
The flow like changes. Like,
Yes, but the ground stays the same. So his question was, well, since it's alternating current, since it's going plus and minus, don't your live and neutral sort of flip? That's kind of what you're asking me. No. The potential relative to ground for neutral is always essentially zero. Live will go above or below it. But the ground point reference of neutral should be relatively close to 0. In an ideal world, it's 0. Okay? There was a question over here somewhere. Okay. All right. Okay. Yeah, back. No? Okay. All right. So that's the basic idea then of how we talk about voltage. And so we've now introduced an important concept. Voltage does not mean an absolute number. It is a difference between 2 points. Why is it a difference? It is a difference because it represents let's say I were to take a unit of charge, which is a coulomb, some unit of charge, and I were to move it from point A to point B, where point A is at one potential and point B is at another. The difference in those potentials, or the difference in those voltages, is the change in energy that unit of charge would go through by that move. So, if I were to take excuse me, if I were to take the charge from point A and raise it to point B, and its potential and the energy was increased, that would mean that's at a higher voltage. Okay? If it decreased, it was a lower voltage. So it's a measure then of the energy difference between 2 points for a charge that's moved between those 2 points. So let's think about what that means. Let's think about it qualitatively first. Based on that fact, can you tell me why current flows from positive to negative? Why do we say current flows from positive to negative? Yeah.
No, I'm not going to ask.
Okay, that's fine.
Just the question, what would be an increase in voltage? Can you give an example?
An increase.
The difference of the voltage between 2 points.
Right.
Or an increase or a decrease.
Okay, so let's take an example. Let's say point A is at ground. Okay? So it's at earth potential. And I take a charge, some box of charge, and I put it at a new point, and I measure, and it turns out when I move it from ground to this point, I find that its energy has increased. What does that mean? That means that point is at a positive voltage. If I took it from ground and I found that the energy decreased to move it to this new point, that means it's a negative voltage. Okay? Now I'll give you an example that will hopefully clear this up, and this is related to the question. So, I took it from ground and I moved it up to this point, and I said the energy increased, which I said meant it is at a higher voltage. Why does current flow? I've now given you the information to answer why current flows between 2 points at a different voltage. Yeah?
Always helps like minimize the energy.
Correct, it's energy minimization. That's exactly what it is. So now you've got an idea of what voltage means physically. Voltage is related to the energy difference for a charge between 2 points, and current is the means by which the charge is minimizing energy. It's trying to get from the high energy point to the low energy point. Okay? It's exactly analogous to having a bucket of water here with a pipe connecting it to a bucket of water here. The water tries to get from the high point to the low point. Okay? The reasons for that is related to gravity. The reason for the change in potential in electric systems is because of potential energy, where the potential is electrical potential, which is voltage. Okay? Yeah?
So how does the low to high happen?
How does what do you mean?
You said it inspires from high to low.
Uh-huh.
how
So there is no current from, that's the point. Current doesn't flow from low to high.
Okay.
Right? Current goes from high to low. Electrons go from low to high. Current goes from high to low. Okay? That's why we'll always say electrons always try to go from negative to positive. Current always flows from positive to negative. Okay? Okay. So that is what voltage is. And remember, it's a relative quantity. If I tell you a system has a voltage of 10 volts, and I just tell you that, that'll nominally mean, I haven't said it very clearly, so if I give you an arbitrary number without giving you a reference for the relative point, that would usually mean it's reference relative to ground. To be totally accurate, we should always, however, say what it's relative to. by convention in electrical engineering, we tend to say, well, that's reference relative to ground. So if I don't tell you what it is, it's reference relative to ground. Okay. Now, I said that that was for a unit of charge. What happens if I have multiple units of charge? Well, if I took 1 unit of charge, and to go from here to here was a certain amount of energy, if I took 2 units of charge, and I moved that same amount, the energy doubled. Okay? Why? Because each of those units of charge, the energy difference added to each other. So, in fact, what we can write is the energy change associated with a change in voltage. The energy change associated with the change in voltage is equal to delta, which is the difference in the change in voltage, times Q, where Q is the charge we are talking about. So if it is 1 coulomb, and we move 1 volt, okay, we will get 1 QV. And I'll explain the units for that in a few minutes. Okay? If I go 2 coulombs and I go 1 volt, we get 2 QV. Okay. So what are those units? We already know what the units of voltage are. We already talked about that. That's volts. And I was named after Volta. What are the other units? The units of charge are coulombs, and the units of energy are joules. So the relationship is volts is equal to joules times, volts is equal to joules divided by coulombs. Okay, that's the relationship. You might sometimes, actually let me ask a question. You should be able to figure this out because you have part of the information in the last class. What is the charge on an electron? 1.6 times 10 to the minus 19 units. Coulombs. Okay. If I take an electron and I move it 1 volt, what is the energy of that electron? It's 1.6 times 10 to the minus 19. Units are joules. Okay, that's correct. If I moved an electron by 1 volt, the change in energy would be 1.6 times 10 to the minus 19 joules. Sometimes you will hear of another unit to describe that. Does anybody know what that unit is? Yeah.
Electron volt.
Electron volt. An electron volt is another unit of energy that we often use. It's called EV. Okay? And that is defined as 1.6 times 10 to the minus 19 joules. Or the energy gained by an electron when you move it by 1 volt. Okay? Good. So that's, an electron volt is a term you may have seen before. I assume most of you have heard of it before. Okay? It's a fairly well-used term in the semiconductor industry, in high-energy physics, in optical communications. Okay. Any other questions? Okay, let's keep this in mind then. We've talked about volts, we've talked about current, we've talked about energy. Let's then start looking at some specific relationships. Okay. I said that the relationship between voltage and charge is energy. So what I can write then is volts is equal to joules over coulombs, or if I write it in a differential sense, it's the voltage between point A and point B is the derivative of the change in energy with respect to change in charge. So it's dW dQ.
That represents what is work, dW.
What's that?
It's work, right?
It's work or energy, right? So work is of course a measure of the energy of the change in energy, right? So that's what we have here. So this is the voltage difference between points A and B is dW dQ between those points, evaluated between those points. Okay, so if I give you a box, some circuit, could be a battery, could be something else, and I tell you the voltage between point A and point B is 12 volts. What that means is dW dQ evaluated between those 2 points is 12 volts. Yes, question.
The reason that we show it with the W as the work, this is the work that can be done with the 2 points, like the voltage.
Correct. Correct. So remember, if you are changing energy, which is what I just did in my example, to change energy, you have to do work.
Between 2 points.
Between 2 points. It's the work done to go from point A to point B. That's exactly right. Okay? Now, but remember something important. Voltage being a relative measure, it depends on your reference. So if I'm referencing relative to point B, I would say point A is at 12 volts. If I'm referencing relative to point A, then I would say point B is at minus 12 volts. Because it's all relative. It's just about how much energy change there is, how much work you are doing. Okay? So you should keep in mind that if you flip the orientation, remember to flip the sign for your voltage. And that's going to be an important rule that you'll do when you start doing circuit analysis. Okay? Because you will find times when you're counting voltages in the opposite direction to the way the voltage was defined. Yes, question.
DQ always positive there?
Well, it doesn't have to be, right? For example, if I take an electron versus a proton, right, and I move between the same 2 points, the work I do will be positive in one case and negative in the other. Okay? So, but it's dQ is defined relative to a positive unit of charge, 1 coulomb. Okay? Okay. So that's voltage. Let's take our first resistive circuit and let's figure out excuse me, how we deal with voltages. So, I will give you a circuit. And this is the circuit I'm giving you. It has one of these. What is this? It's a battery. So a battery is usually drawn as 2 parallel lines, one shorter than the other. By convention, the shorter one is called the negative. The bigger one is called the positive. And I will have 4 resistors drawn over here. So there's some circuit that I've given you. And I want to start defining some reference points so I can start doing circuit analysis. We'll get to the circuit analysis today, but all I want to do for now is just define reference points. By convention, it is usually easiest to pick 1 point and call it 0. If I give you a battery, I'll take a 9-volt battery or something like that, I'll give it to you. And I'll say, what's the voltage on this terminal? Let's draw a battery, okay? We'll take a 9-volt battery. These are what our 9-volt batteries roughly look like. And I will ask you to tell me the voltage on this terminal. What is it? What's that? Thank you. That's the right question. I didn't ask you. It's whatever it wants to. Let's say I take that 9-volt battery and I licked it. Okay? But I didn't lick both terminals. I only licked one. What would happen? Nothing. Nothing. Because it's isolated. It's sitting up there. It's not relative. Now, I'll drink a little bit of beer. I'll have a few friends over. We'll start having challenges about what we're willing to lick. And I lick both terminals at once. Now what happens? Yeah, you get a little shock. You ever tried that? Anybody tried that? Licking a 9-volt? How does it feel? Yeah, it's okay. It's not bad. 9 is okay. Okay. I once licked a capacitor that was charged with 40 volts. That was not so good. So it's all relative. This is the point. So this battery, knowing the voltage, is useless unless I have a reference. It doesn't matter what that reference is. I could choose to call it 100 volts. I could choose to call it 50,000 volts. It doesn't matter. But to make our lives easier, so that we don't have to add 100 or 50,000 to every number, we typically will pick 1 point and call it 0. It's often easiest to pick the negative end of the battery and call it 0. That's often what we do. So we will call this point 0. That doesn't mean it is actually at ground unless we tie it to ground. If this is just a circuit sitting in plastic that's completely isolated from ground, it's not actually at ground. But it's convenient to call it ground so that all our numbers are referenced relative to 0. So we'll call it 0, and then we'll define other points. Now, what are the points that we define? Any point which is an intersection between two components, we call a node. Okay? And I'll call this a node 1, and I'll call that node 2, just for convenience. Okay? There are a few other nodes here, okay, that I haven't shown. I'll explain why in a minute. Of course, in this section and the next section, what are we going to do? We're going to teach you how to take this circuit and figure out what it actually does by eliminating nodes. By writing equations that allow us to say, well, we don't need to keep track of what's going on in node 1 and node 2. Let's simplify it to something equivalent. And that's what our goal is going to be. Okay? Yeah.
So the ground doesn't necessarily have to be at that node, does it?
No, you do not have to place ground here. You could choose, just because you want to do it that way, to place the ground up here. That would be fine. You can place it anywhere. It just means all your equations have to be written. If you decide to put a 0 into your equation for some reason to represent a voltage, remember the 0 is that point. Okay? It's easier to put 0 here for two reasons. One, it's close to the negative of the battery, which means the battery voltage, let's say this was a 9-volt battery, then 9 means 9. 9 doesn't mean something else. So it just makes life easy. That's why we do it that way. Okay, but it's up to you. You could, in theory, do it how you want it. Let's not make your life difficult, right? Usually try to make your life easy. So it's my job to make your life difficult. So, all right. Now, I've been talking about voltage and current. Let's talk about how we actually measure these things. Okay, how many of you own multimeters? A remarkably small number. You should go and get multimeters. They're cool things. First dates with a multimeter in your hand is the best thing, man. So, no, I'm kidding. But no, a multimeter is a useful thing. I mean, you can use them. They're quite cheap. And multimeters, so you own a multimeters? Did you put your hand up? Okay. Someone put his hand up over here. Come on, I'm going to pick on one of you. Yeah, okay, there you go. You own a multimeter.
Yeah.
It has, what all functions does it have on it?
It has square wave for voltage, resistance, and then
DC voltage.
yeah, DC and AC.
AC and current as well?
Yeah.
DC and AC current as well. Okay, so a typical multimeter can actually do multiple things. It can measure voltage, it can measure current. Cheap multimeters today are remarkable. They've gotten so cheap, it's crazy. They can measure resistance, some of them can measure capacitance, some can measure temperature. Okay, they can do a lot of useful things. So, how do we measure the voltage? Let's say I give you a battery. I give you this 9-volt battery, and I ask you to measure the voltage on the battery. What would you do? The multimeter has two terminals, two leads. You touch one lead over here, the other lead over here. You'd make sure that it's set on the voltage range. That's very important. It needs to be set on the voltage range. And you'd measure the voltage, and it would say it's about 9 volts. Okay? And if I gave you this resistor, and I asked you to measure the voltage across this resistor, you'd do the same thing. You'd put one lead over here, you'd put one lead over here, and you'd tell me the voltage. Okay. Let's think about this problem a little. How many of you have heard of the uncertainty principle? What does it say? At the back. Yeah. What is the uncertainty principle?
I've heard of it.
Okay. Good credit, man. That's the perfect answer. Try that on a test sometime. Okay, all right. Anybody want to give me, what's the uncertainty principle?
That you can know the place and speed of an electron at the same time.
Okay, good. That's a very good way to say it. We cannot know the position and energy or velocity of an electron at the same time. Perfect statement. Okay, that's a precise way of saying it. Another way that is often described is we'll often say that it's impossible to do a measurement without perturbing the system. That's a consequence or an indirect of the uncertainty principle. In other words, if we want to measure a system, we always perturb it. Voltmeters, or ammeters for that matter, have similar things we need to deal with. Okay, so, excuse me. If I want to measure the voltage across this resistor, and I put a voltmeter across it, what property would I want that voltmeter to have such that I don't mess with the resistor? Yeah, I want it to be really, really high resistance. Ideally infinite resistance. So that the resistance of the voltmeter doesn't mess with the resistance that I measure over here. So voltmeters should ideally have infinite impedance. They typically don't. Typical multimeters will have input impedances on the order of 10 megohms. Okay, that's pretty typical. So it's a large number, but it's not an infinite number. That's pretty common. So a voltmeter should have a really high resistance. The idea being, if it has a really high resistance, it doesn't draw much current when it makes the measurement. So it doesn't draw much energy out of the system, so it doesn't perturb the system. So a voltmeter would have it measures voltage in an ideal world without drawing any current. In practice, it draws a tiny amount. Okay, if I took a 1 volt actually let's say it's a 10 mega ohm voltmeter, and I measure a 10 volt battery. How much current does it draw from the battery when I measure it? 1 microamp. Good, I was just seeing if you remember those numbers. That's right. Okay? Okay, good. So now an ammeter is a little different. An ammeter is used to measure the current flow through a circuit. To measure the current flow through a circuit, we have to put it in series with the circuit. Okay? And we put it in series with the circuit so it can see. It's like connecting a flow meter to a pipe. You want to measure the flow through the pipe, you would want to put a flow meter on the pipe so you see how much flow goes through it. It's the same sort of deal. That's what an ammeter does. Now, for that situation, what would you want the characteristic of the ammeter to be? Would you want it to have a really, really high resistance or something different? Very, very low resistance, ideally 0. In practice, we do not get ammeters with 0 resistance. A cheap multimeter, in fact, the ammeter is worse than the voltmeter. The voltmeters are pretty good. 10 megohms, in some cases actually teraohm. So very high numbers, or gigohm. But ammeters typically, cheap ammeters will have a resistance of 0.1 ohms. So that's not that low. It's enough that it actually does perturb circuits with very low resistance. Okay? So this is why you do not want to take your multimeter in an ammeter range and put it across your battery. Because that means you're putting a 0.1 ohm resistor across your battery. What happens when you do that? It's essentially a short on your battery. Most ammeters have short circuit protection, so the ammeter will be fine. The ammeter won't get damaged, but you'll discharge your battery relatively quickly. So, and it'll heat up a little. So that's not so good. Okay, so we measure voltage by putting a high resistance across what we are measuring. We measure current by putting a low resistance in series with what we're measuring. So I'm going to rephrase that again in terms that are electrical engineering terms. We measure voltage by putting the measurement unit in parallel with what we are measuring. Okay? We measure current by putting the ammeter in series with what we are measuring. And you all know what those terms mean. We're using it the same way those terms are used in common English language. Okay? So that is how we measure voltage and current. Anybody know how we measure resistance? If you took your multimeter, or any of your multimeters, and you put it on the resistance mode, and you measure resistance, how does it work? Yeah? Yes, perfect answer. It actually puts a small current through it, and it measures how much voltage is generated. And then it uses Ohm's law, which we're going to learn about in a minute, to calculate. Because you know the resistance is related to the current and voltage in direct proportion. So, put a known current through, measure the voltage, that's a measure of resistance. That's the way modern multimeters work. Early multimeters actually would put a known voltage and measure the current, but that's an inverse function, which is not so easy to calculate. So you gave the right answer. Okay. So that's how we measure resistance. Anybody know how we measure temperature? Those multimeters that we use. This is not so obvious. Any of you? Yeah.
So when material heats up,
Uh-huh.
resistance changes.
Uh-huh.
So you know the characteristic property of the metal that you're testing, then when your current goes down, if your resistance is going up,
Uh-huh.
and you can tell the other guitar.
That's a good answer. That's actually not how they do it in cheap multimeters, but that is one perfectly valid way to do it. What he said was the following. most materials, the resistance is a function of temperature. Which means as temperature goes up, resistance typically goes up. Okay, for most materials that we deal with. Which means if you measure the resistance of a material that you know about, and you take that number, if you know the properties of that material as a function of temperature, you can calculate temperature. That is nominally how you could make a thermometer. But in fact, it turns out that's not exactly what most multimeters use a thermocouple. Okay? And a thermocouple is a device that generates a small voltage difference. And that voltage difference depends on temperature. So it measures voltage directly. That's pretty, most multimeters do it that way. Okay? Yeah, question?
We know ion moves from negative to positive, is that right?
No. Electrons move from negative to positive.
Sorry.
Current is always positive to negative. Okay? So, I know that's not a very satisfying answer. By the way, that's why the British tried to fix it in the 70s and 80s, because they felt they were just confusing people. But we're stuck with it. Okay. So that's how we then measure voltage and current. Now, so I've defined really two terms here. I've defined parallel and series. I'm going to define another two very important terms for you. One term I'm going to define is called open circuit. An open circuit is a case where there is no current flow between the 2 points in question. So, for example, the connection between point 1 and point 0 is an open circuit because there's no wire connecting them together. Okay? A short circuit is where I short out. I put a wire between point 3 and point 4 such that there's a lot of current flow. That's not a precise enough definition. Can you give me a precise definition for short circuit? And by the way, you can just look a little higher up on the page and it's there. So, what would be a good definition for short circuit? Yeah.
Maybe it's a smaller fluid inside the
That's not actually a precise definition for short circuit. Okay, it's not quite there. You've given me a way to say what's a relative measure, but I want a precise definition for short circuit. Yeah, there's no voltage drop. Very good. Good job. Okay? No voltage drop. Because the resistance, you said it right. You said, I want a really low resistance there. That's exactly right. But the definition of short circuit is essentially a zero resistance, so you have no voltage drop. So, open circuit is no path for current flow. Short circuit is no voltage drop. Okay. An ideal voltmeter. Would it be an open circuit or a short circuit? Open, because it's a really high resistance. And an ideal ammeter is a short circuit. Okay? Because it has no resistance. It's got very low resistance. So that's another set of terms. Now, open circuits and short circuits are very useful things to think about because it turns out it's a very powerful construct for simplifying circuit schematics. What we do is we take a circuit and we figure out how it would behave if it were connected as an open circuit, and we figure out how it would behave if it were connected as a short circuit, and then we can simplify it. And we'll learn about that later. That's why we're introducing these concepts now. Okay, so we've talked about energy, voltage, and current. One more thing we want to talk about, and that's power. Okay, so power is the rate of change of consumption or generation of energy. Okay, so it's a rate term. Excuse me. If we were to write it as an equation, we would write power is equal to dW dt, the rate of change of energy or work. Okay? But remember what W is. W was related to voltage, and W was related to current, and W was related to time. So, in fact, we can write, actually let me rephrase that. We have related W to voltage and to Coulomb charge. But remember what coulombs are. Coulombs are the integral of current, right? So it's with respect to time. So I can write dW dt as dW dq times dq dt. Because dW dq was voltage, and dq dt is current. So then power is just voltage times current. Okay? How many of you own microwave ovens? I would assume virtually all of you. All right. Anybody know, typical microwave oven, like the kind you'd have in your room, what's its power rating? Max power? 1,000 watts is pretty, 900 to 1,000 watts is pretty typical for most reasonable sized microwaves. Okay. Can you tell me, using the simple math that we've got before us today, how much current it draws? That's a good guess, on the order of 10 amps, right? Because we said 110 volts, 1,000, so about 10, close. Okay, let's say it was exactly 10. Okay, is the number we have. So we had 1,100 watts, 110 volts, we've got 10 amps. That would be a reasonable guess. Does anybody know, is the actual current more, the real current, is it more than that or less than that? Anybody know? You probably haven't learned about this yet. It's actually a little bit more. Okay? And the reason it's more is there's something called power factor correction, which describes the time lag. These are AC signals we're talking about. And it describes the time lag between the voltage and current. Okay? And so most systems actually are not power factor corrected perfectly, so they actually consume a little bit more. Don't worry about that. You won't learn about that in this class. I don't think. To be honest, I haven't made notes all the way to the end of the semester, so I don't know if you're going to learn about it. We'll see. Okay, so, but for a DC system, for a system that doesn't have AC, P is exactly equal to V times I. Because we're not dealing with relative time-dependent changes. So if I give you a DC system, I put that thing on my tongue, and I ask you, what is the power being consumed by my tongue? Pretty easy. You know the voltage in the battery, you get an ammeter in series with that, you measure how much current it's drawing, and you can say, at this instant, your tongue, which is slowly turning brown, is consuming X number of milliwatts. Right? And it's probably going to, my guess, if I had to, actually it'll be more than that. A 9-volt battery typically maxes out at several tens of milliamps, just because of its internal resistance. So it's probably going to be on the order of 100 milliwatts to a watt, something in that range, which is enough to start killing cells. So, you know, it's kind of fun to do, especially when you're a little drunk, but don't do it. Okay? So it's on the order of, that tongue experiment was on the order of 1 watt. Okay? You got a good definition for a watt. It's the amount of power your tongue burns when you put a 9-volt battery on. Okay, so that's a watt. So last couple of things to do. Then we're going to switch gears for a minute. We have enough time that I want to give you a side example. At the end of each section, I'm going to try to give you a side example, just for fun. No notes. We'll just pick an interesting application and we'll talk about it. In some cases, I'll suggest one for you to think about. Other cases, I'll ask you to come up with an idea and then we can just talk about it. You'll see what I want to do, okay? All right, so that 9-volt battery, I said something interesting about it. I said it's a 9-volt battery, but I said when I put it on my tongue, it kind of tops out at the order of 100 milliamps. Okay, that says something about that battery. It's not an ideal battery. Let me explain why. If I gave you a battery that's like this, it's just a voltage source. Okay? Let's say it's a 10-volt battery. And I put a 1-ohm resistor across it. How much current should flow? 10 amps. Okay. If I put a 0.1-ohm resistor across it, how much current should flow? 100 amps. In theory, I could keep going. If I put a 0-ohm resistor across it, how much should flow? Infinite current. That battery didn't work that way, right? That battery started topping out at about 100 milliamps or so. So that's not a perfect battery. Real voltage sources are always actually this. In other words, they are a battery with a resistor in series. And that resistor value is usually pretty low. So for normal situations, we can ignore it. But when you do something dumb, like put it on a very low resistance like my tongue, or with an ammeter going directly across it, that resistance matters. And so what makes it top out is, what you've really done is put your tongue in series with that resistor. And so even if your tongue is a really low resistance, this resistor is not, and that sort of puts an upper limit on how much current you'll get. Okay? So, this is some nomenclature that we use. we model DC sources, ideal sources. We typically draw it like this. Sometimes you'll see it drawn like this. Okay? The capital V indicates that it's DC. A non-DC source, a source that could be AC, will typically use a small v. And that indicates it doesn't necessarily have to be DC. Real voltage sources will always have a resistor in series with them. Okay? So those are the types of voltage sources that we have. Current sources, excuse me, current sources we model as a circle with an arrow. And the arrow points in the direction of positive current, which means the current will come out this way. Okay? And similar rules. DC current sources, usually marked with a capital I. Any type of current source, AC or DC, marked with a small I. Now, let's flip the problem. Let's say instead of giving you a battery, I gave you a current source. And I put one end over here and the other end of it here. What's going to happen? What am I going to measure? Let's say, and then I ask you to measure the voltage. Okay? And let's say I put a 1 amp current source here. And I measure the voltage. What would I measure? Anybody know? It depends on the resistance of your tongue. It's going to, by the way, what is going to happen is it's going to start out at a really low voltage and then it's going to go up as your tongue burns. Okay? 1 amp is enough to burn your tongue. So that's not such a good idea. All right? So, but it turns out all current sources, why does the resistance go up as your tongue burns? Anybody know?
Water.
Yeah, you're evaporating all the water and your tongue starts carbonizing. Okay, so all these useful things you're learning in this class. That's amazing. All right, 3 classes in, and what have you learned? You've learned how to piss off your landlord and how to burn your tongue. So, all right, so this is a current source, but all current sources also have limits. They're not real. Okay, they're not ideal. And in a current source, the way we model that is by putting a resistor in parallel. And what does that mean? That means that even though the current source nominally, what does a current source mean? A current source is supposed to be a device that can provide that current no matter what. If I put a 1 ohm resistor across it, I would get 1 amp. If I put a 100 ohm resistor across it, I would get 100 amp. I would still get 1 amp. If I put a mega ohm resistor, I should still get 1 amp. In practice, that's not what happens. For low resistances, it will provide the current it's supposed to provide. But as I start putting a higher and higher resistance across it, at some point, it's not able to provide the current. The reason is, it's really a current source in parallel with another resistor. So if I put a low resistance across it, no problem. This resistor doesn't matter. This resistor has a higher resistance than this. But if I put a really high resistance across here, then most of the current just flows through here, and I don't get as much current as I wanted over here. So, an ideal current source, what is the value of this resistance? No, infinity. And an ideal current source, the value of that resistor is infinity, such that no matter what resistor I put over here, the current always goes through this resistor. Okay? If I have a real current source, this is a high value. It might be mega ohms or tens of mega ohms, but it's not infinity. Okay? So this is the key point. Let's go through it again. In a voltage source, what is the ideal voltage source? What is the value of that resistor? 0. Because we don't want any voltage drop across it. In an ideal current source, the value of this resistance is infinity because we don't want any current going through it. Okay? So we've now defined the reality and how we typically proceed. Not all voltage and current sources are what we call pure sources in the sense that they have fixed values. I will give you a 9-volt battery, that's a 9-volt battery. I could give you a 1 amp current source, that's a 1 amp current source. We have other sources that are called, dependent sources. Dependent sources will be sources where the voltage or current depends on some other variable. Let me draw an example. I will give you a voltage source, and I'll use this example right over here, a voltage-controlled voltage source. And I will tell you that this source on this output produces 10 times the voltage measured between these 2 points, point A and point B. Okay? So 10 times V, A, B. So if I put 1 volt across point A and point B, I'll get 10 volts over here. Okay? If I put 2 volts, I get 20 volts. Can anybody give me another name for this particular example that I've given you? What was it? It's an amplifier. This is an amplifier, right? It's amplifying whatever I'm putting in. That's right. Okay? So, that is an example. This is called a voltage-controlled voltage source, where the voltage it produces depends on the voltage on some control pair of terminals. We can also have the other types. We can have voltage-controlled current source, where the current depends on the voltage, current-controlled voltage source, where the voltage depends on the current through some other pair of terminals, and so on and so forth. Okay? These actually exist. We make them. Okay? This is an example of a typical amplifier. These are actually examples of specific devices that we will look at to some degree in this course. Okay? All right. Okay. Let's then, let's use the board to explain what I'm about to explain over here. Let's say I give you an ideal voltage source. Okay, this is your ideal voltage source. And I ask you to give me a plot of, I'm going to ask for 2 plots, okay? One plot is going to be a plot of the voltage as a function of time, and I'm going to connect this across some resistor, okay? And the other one is going to be a plot of voltage as a function of current. Okay, this is the ideal voltage source connected across a resistor. And let's say the voltage on this source is 10 volts. What does this plot look like? It's voltage as a function of current. So current is the current through this, I. V is the voltage through that. Okay? And this resistor I can vary, okay? It doesn't matter. I'll give you a knob that you can turn, do whatever you want, change its resistance. I just want to know what the voltage will be as a function of current. I understand why you said dot. That's why I just changed it to a variable resistor. Okay? Yeah, back. It will be linear, but how will it be linear? Will it be going up like this? It'll be parallel to the x-axis. It'll be like that, because this is an ideal source. So no matter how much current I draw, this always gives me 10 volts. Okay? Correspondingly, an ideal current source would be something like that. It'll always give me the current that I request, no matter what resistance or voltage I apply to it. Okay? Real sources are not perfect. So, let's take that 9-volt battery. We'll call it a 10-volt battery for convenience. And it has a certain internal impedance. That's our RS, our resistor in series. And here's my tongue. Okay? All right. What does this curve look like? And my tongue resistance changes. Okay, so you can tune my tongue to vary the resistance. So I generate this curve. What does it probably look like in reality? It's probably actually going to be something like that. Okay? And it'll drop off. Okay? And this is the point where, in fact, I said it was on the order of 100 milliamps, and it's like here. Okay? That's probably about there. Okay? So, these systems tend to be treatable as ideal over certain ranges of operation, but not overall. What would be the condition for that tongue circuit over there where I could treat this as ideal?
less than the resistance is high enough
Yes, he said when the tongue's resistance is high enough, that's a good answer. What is high enough?
compared to the general.
Yeah, when the tongue's resistance is much higher than RS, I can treat it essentially as a voltage source, as an ideal voltage source. Because even if, let's say my tongue's resistance is a mega ohm, and this resistance is 0.1 ohms. If the tongue resistance went from a mega ohm to a kilo ohm, it doesn't matter. It's still so much more than the 0.1 ohm internal resistance that I can still treat it as being a perfect voltage source. Okay? So we often do that. We often take real sources which aren't perfect and we treat them as perfect. We've now introduced an important concept. We've introduced a concept of current versus voltage characteristics, often called IV characteristics. And what we do in a current versus voltage system, you will change the voltage and you'll measure the current, or you'll change the current and you'll measure the voltage. And that's how we tend to do these things. Okay? So that's basically how this works. For a current versus voltage characteristic, okay? For a current versus voltage characteristic, what does the slope indicate? And I'm going to ask you here. If I take this slope, okay? And remember, so the slope of that is dV di. Right? What is that? The units of that slope. So remember, V is equal to IR, so R is equal to V over I. Good. Okay? That's units of resistance. If I had the opposite plot where I had I here and I had V over here, what would that be? What would the slope be? Inverse of resistance, anybody know what that's called? Conductance, actually. Okay? Conductance. Conductivity is a characteristic of conductance. Okay? So conductance, what are the units of conductance? Anybody know? Yeah, there's both. It's the same thing. We use, Siemens is the right answer, but in electrical engineering, someone very clever said, well, it's the opposite of ohm, let's call it a mho. Okay? MHO. If that's true, I mean, I'm not kidding. That is actually what we use. Okay. Let's take an example. Oops, sorry, too far. Let's take an example. And the example I will take will be a circuit over here. And it's a 10 volt. We're going to do our first circuit analysis. It's a very simple one. It's a 10 volt circuit. And I've got a 2 ohm resistor here, a 5 ohm resistor here, and a current controlled voltage source here. Okay? And what I want to do is I want to know how much voltage shows up across the voltage source. I've picked the numbers this way for a particular reason, okay? To make life easy. So I've got a 10 volt voltage source, and I've got a 2 ohm resistor here. What is the current in this loop? It's 10 volts divided by 2 ohms, so that's 5 amps, okay? And my voltage source over here, I've said the voltage I get is 4 times I1. So it's 4 times 5, so it's 20 volts. I've cheated. I've picked the number so I could do the analysis as easily as I did. You'll understand why I cheated in the number, okay? But not today. You'll understand it in the next class. So that's that. This is an example of a very simple analysis. I took a circuit. I asked, what's the current? Then I put it in there and I calculated this voltage. There was a lot of little things I did, and you all went along with me. And the reason is you've already internalized some of the things I said. Either that or you didn't care. Okay? So I said 10 volts, but I had automatically chosen a ground. What was the ground that I picked? I picked this as my 0 point because I said 10 volts. 10 volts is really only between the 2 points on the battery. So you see how we internalized that. We automatically picked it. We went with that. And then we calculated current, and then we figured everything else out. And then when we provided this voltage, again, we referenced it relative to this point, which we call ground. It was convenient. It's the negative of both of these sources. It's convenient to call it ground. That's why we did it that way. Okay. So that's that. So we're done with this section. We have about 5 minutes left. So let me introduce, at the end of each section, do you have a question or you're okay? Okay. So at the end of each section, I want to have a discussion about a random electrical engineering device or application. Sometimes I'll know the answer, okay? Sometimes, like today, I might choose to give you an example, okay? One second. Other times, I will ask you to suggest something. If I can tell you about it, I'll tell you about it. If I can't, I'll tell you I don't know. Okay, yeah, go ahead.
I just have a quick question. So what's the 5 ohm resistor doing up there?
I put that there to make my math work, okay? Don't worry about it now,
Okay.
okay? If I hadn't put it there, the current through that central resistor would not have been 5 amps. Okay? You'll see why in the next class. I put it there to make my math work. Okay. So let me ask, do you have any devices you'd like to talk about today? Yeah. I'm sorry? What's that? How can you disable a subwoofer without touching it? Why, you have a neighbor who drives you crazy or something? Okay, well actually, so that's, how could you, okay, I can tell you how to do that, okay? I can actually tell you how to disable a subwoofer without touching it. I will suggest 2 ways to do it, both of which if you can do, I will be very impressed, okay? So, so anybody have any ideas? Your neighbor has a subwoofer and it's driving you crazy, you want to disable it. How could you do it? Yeah. What's that? Okay, ask them to turn it off. That's pretty good. Okay, very good. He's got a good one. So, anybody knows what a loudspeaker is? What is a loudspeaker? So a loudspeaker, at least a subwoofer. One day I'll teach you about really good loudspeakers. I'm kind of a speaker nut. I collect speakers, okay? Yeah, my wife really loves this hobby of mine. But no, I collect loudspeakers. I have a lot of different types. A subwoofer is typically a very simple cone speaker system, okay? It's a paper cone. Well, in a well-made speaker, it's a paper cone. In fact, most subwoofers that you deal with are plastic, okay? And so they're plastic cones, very light, and they have a coil and a magnet behind them. When you apply, you probably learned this in high school physics, when you apply a change in voltage on the coil, it generates a magnetic field, and that causes the magnet or the coil to move relative to each other. And so we produce sound by making that coil or magnet, typically it's a moving coil system, move back or forth, and that moves the paper, which pushes air and you get sound. Okay, so how could you destroy? Let's make a subwoofer bazooka. How could you destroy it? Anyone got an idea? Yes?
Generate like a strong enough pulse so that it's part of the entire circuit.
Okay, first we could make an EMP. Okay? Unfortunately, it would probably take out a lot of other stuff around it. An EMP would be a system where we generate a huge electromagnetic pulse. It'll burn out that coil. Very good. That's a good idea. Okay, yeah.
Did you just need the cup to go too far?
Yes, you can. That's the other way. You just make the cup move so far that it's not able to move back, or better still, it tears.
Right.
Okay? How can I do that? This is our bazooka. We get in there. Yeah.
Buy a laser pointer and burn a hole in the...
Yeah, I don't know what laser pointers you have access to. That is a good idea. You can use a very sharp, a focused energy source to burn the cup. Now, a laser pointer is good, but you know, it's hard to get something that's that focused and can burn plastic or paper. Any other ideas? Yeah.
You could lock the whole thing inside a wind tunnel?
Yes, he's getting to the idea. If we have a focused wind source, okay, the paper cone actually acts like an amplifier. The problem with a laser pointer is that the cone's not really designed to absorb lasers, right? So you really have to hit a focused beam and get it to burn. But that cone is designed to move air, which means it's very sensitive to air. So if I could take a really high-speed, high-velocity beam of air, okay? And they got their car window open and you aim it just right, you will blow out their subwoofer. That will work. Okay? All right. Any other ideas? Yeah. What?
Firearm.
Yes, that's true. Firearms solve a lot of problems. Yeah.
Do you use a large enough magnet to mess with the internal magnet?
Yeah, but then you'd have to, yes, if you could. That is a good idea. You could put a really strong magnet behind it, and that would lock the coil and prevent it from moving. But you've got to keep the magnet there.
And if you're willing to do that, that's fine, but at some point the guy's going to be like, why the hell is my subwoofer on? So,
Use a cup of water.
yeah, so a couple, to do what?
Either goes, basically, correct the circuitry or it's paper. You could
Yeah. Okay, so both ideas are good, okay? One idea would be to use a cup of water to sort of short out the coils and corrode it. You'd want to use salt water, not regular water, but it would work, and that's not a bad idea. The other idea was that it's a paper cone filter. I mean, a paper cone system would be really sad because paper cone speakers are actually really expensive. Good paper cone speakers are really expensive, but you could essentially make the paper sort of fall soggy and fall apart. By the way, the best paper cone speakers were made in Japan. Anybody know what they used to moisten the paper to get it in the right shape? Sake! That's right. No problem. Alcohol cannot solve that. Okay, so we'll stop right there. We're done. We'll pick up on the new section. If you haven't got a handout, please take it.